You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Paul Davies. Paul Davies is a theoretical physicist and Regents Professor at the Department of Physics at Arizona State University. He is a cosmologist, astrobiologist, and best-selling science author. His research interests have focused mainly on quantum gravity, early universe cosmology, the theory of quantum black holes, and the nature of time. He has made important contributions to the field of astrobiology and was an early advocate of the theory that life on Earth may have originated on Mars. Among his many awards are the 1995 Templeton Prize and the Faraday Prize from the Royal Society. He was made a member of the Order of Australia in the 2007 Queen's Birthday Honours list, and the asteroid 6870 Paul Davies is named after him. His more recent books include The Demon in the Time Machine, About Time, The Origin of Life, How to Build a Time Machine, and The Eerie Silence, Are We Alone in the Universe?
Paul Davies, welcome to the program.
Thank you.
Now, Paul, for many, many years now, you have worked in some very interesting areas of physics, cosmology, but also the origins of life. And I think that's a good place to start is how did this come to be, this world in which we live with all of these living species and even consciousness? Going back to the very beginning, are we any closer? Let me ask it this way. Are we any closer now than we were during the Urey Miller experiments, where do we really know anything more about abiogenesis than we did 50 years ago?
Not very much more, I might say. And let me presage my further remarks by saying that I've worked for much of my career on the origin of the universe. And I think that's a lot simpler than the origin of life. And part of the reason for that is that the universe is actually very simple. It certainly started out in a very simple state, whereas life is incredibly complex. So somehow a mishmash of chemicals turn themselves into a living thing. And we have no idea really how that happened. It seems reasonable to imagine there's a long pathway of increasing complexity with molecules participating in all sorts of chemical cycles and things. But we don't know the details of that, and we're so ignorant of it that we can't even say whether this is something very likely to occur or very unlikely to occur. So if you have another Earth and sort of try to rerun the movie, will life happen on this other Earth-like planet given the same conditions? We don't know the answer to that. And it's a curious thing that when I was a student, which I have to say was many decades ago, I was a passionate believer in extraterrestrial life. It seemed to me that this was inevitable, that there would be life out there. And I couldn't find any of my scientific colleagues to agree with that. One might as well have professed an interest in looking for theories. It was just considered obvious that life was an incredible fluke, a chemical accident of such stupendous improbability, it maybe only happened once in the entire universe. And yet, over the decades, the pendulum swung the other way. So by about 1990, and in particular when NASA created the Astrobiology Institute and the subject of astrobiology became very fashionable, then people started saying, oh, the universe is teeming with life. But the evidence hasn't changed, frankly. We haven't discovered a single case of life beyond Earth, so we know of only one sample of life. We know it happened once. We don't know it's ever happened again, and we don't know how to put the numbers to it. And so I think we're very much in the dark about how non-life turned into life.
Part of the problem here is that the chemistry of life, when you're looking at DNA and RNA, it is very, very different from normal chemistry, which can be fairly straightforward, not always, but this is something orders of magnitude different than anything else we know of in chemistry. Now, you have suggested, and other people have suggested, that there may actually be a quantum mechanical component here that either may have been involved with the genesis of life, but also the functioning of life. Could you give us an overview of those ideas?
I've come at this point of view rather gradually over the decades. I was much influenced by Erwin Schrödinger's little book called What is Life, which was written remarkably in 1943, in the height of World War II. Schrödinger was a refugee from Nazi Europe, and he was sheltering in neutral Ireland and was able to give a series of lectures called What is Life, and then wrote a book to go with it. It was very influential. I read it as a student. Now, the reason I mentioned Schrödinger is he was the architect of quantum mechanics. And so, in a sense, he'd solved the problem of matter back in the late 1920s, because quantum mechanics explains the nature of matter all the way from subatomic particles right up to stars. But it leaves out of account living matter. He was unable to explain life with quantum mechanics, but he sort of felt that it should have something useful to say. And that was the content of his lectures in 1943. And so I became influenced by that, but it seemed to me that mostly ball and stick models of chemistry would be adequate to explain what had happened. And over the years, I've become more and more skeptical that that is the case. And it seems to me, well, if I should repeat Schrödinger's own words here, that some new kind of physical law is prevailing in living matter. That's the way he put it, a new kind of physical law. We must leave ourselves open to that possibility. And it's a rather drastic step for a physicist to say that the existing laws of physics are inadequate to explain something. If you go to a physics department, typical physics department, and say, can physics explain life? You'll always be told, well, yes, of course. But then if you ask the question, well, can known physics explain life? Well, that's not so clear. And I've come to the point of view that we need to go beyond known physics to some new kind of physical law, as Schrödinger suggested it. Now, I think that new kind of physical law would have quantum mechanics as an integral part of it. But I've taken the point of view, which I've arrived at over about the last 10 years, that the fundamental distinguishing feature of life is information. It's that life is complex chemistry, of course, but the thing that makes life stand out is the way it stores, replicates, and processes information. And you mentioned DNA. Of course, that is the informational molecule, as was obvious right back when its structure was elucidated in the 1950s. It carries the genetic information, the blueprint, if you like, the instruction set for making the organism. And that information is copied and passed on from one generation to the next. So we're very familiar with life as an information processing system, and even more familiar now, I might say, with the advent of gene editing technology. We can rewrite the book of life. We can go in and change some of the letters, some of the words, and make organisms to order. This is now part of commercialized technology. So the idea of life as basically software as well as hardware, I think, is becoming pretty thoroughly established. But that to me suggests that you don't solve the problem of life's origin just by figuring out how to cook up complex chemistry, even how you cook up molecules like DNA, for example. The thing you also have to explain is the origin of the software. And I don't want to belabor this too much, but if I give you an analogy, to a physicist, life looks like magic. When I see all the things living organisms do, you think, well, that's absolutely astonishing. Of course, I don't think it really is magic, but it looks like magic. But I have the same impression with my computer. It seems like magic what it does. And I can remember the early days of personal computers thinking, well, how does it do that? And we've become so used to it that we tend to take it for granted. But if you take something like PowerPoint or Photoshop or something like that, it is incredible what can be done. Now, if I go to a university, the computer science department, and say, explain to me the magic of my personal computer, and if the answer entailed taking the back off the computer and looking inside and saying, well, there's some silicon in here and some copper, and it's sort of complex patterns that we haven't quite figured out the details, but it's got something to do with silicon and copper and plastic. Well, you'd know that was a ridiculous answer. To explain the magic of PowerPoint or Photoshop, you talk to a software engineer and they tell you all about the code and how it was written and all the bits of code fit together and so on. So the origin of Photoshop is not to be sought in plastic and copper and silicon. It's to be sought in the encrypted version of software. And life uses an encrypted version of software as well. The book of life is written in a 4-letter alphabet in DNA, but the implementation is in a 20-letter alphabet that proteins use. They're built of 20 amino acids. And there's a translation, which is the same. The code that translates from the encrypted 4-letter data set to the 20-letter data set is universal to all life on Earth. And that is very typical of what we would normally regard as a communication channel in digital engineering. There's input data, there's an encryption, there's a decryption, and then there's an output. And so all of that sort of software stuff that we've become used to from computing, we have to import that into life as well. And we won't understand life's origin without understanding the software as well as the hardware.
Could it be argued that life, in addition as an information storage medium, it's a very good one, meaning that it can preserve through replication information for millions of years? So could it be said that it's actually the most efficient preservation method of information in the universe, essentially, as far as complex information? Could that be said?
Well, it's certainly true that life is very good at the information thing. It's often, we use the expression, as old as the hills, but actually DNA is much older than the hills, and a lot of the genes in your body and mine are essentially unchanged for 3 billion years. Now, of course, what happens is that life deploys all sorts of fancy error correcting and editing techniques. So if you just take a strand of DNA and replicate it, there will be errors, but these errors get corrected. And then if natural selection favors certain arrangements of things, conserving those arrangements, then it will conserve that particular thing. But the other thing that is astonishing about life, it not only has this extraordinary fidelity at copying and preserving, but it does it in an incredibly energy efficient manner. In fact, everything life does has been honed to be right on the edge of what is thermodynamically possible. And the example I like to quote is the human brain, the thing between our ears. That is an information processing system of staggering ability and complexity. And it's got the power of a supercomputer. But a supercomputer might consume a megawatt of power. Our brains do it with the equivalent of a dim light bulb. And that's because information at the level of DNA all the way up to brains has been honed to be thermodynamically not perfect, but very close, in some cases, very, very close to perfection, to the ultimate of what is possible within the laws of thermodynamics.
Now, mutation with quantum mechanics being a potential contributing factor to mutation. Any thoughts on that?
Well, it's certainly true that quantum effects will bring about mutation. There are classical and quantum effects. The issue really with quantum mechanics and life is, in my view, that there are certainly a few clear examples where non-trivial quantum effects are playing a role in life. And let me just clarify this, because in a sense, of course, life is quantum mechanical because life is chemistry, and chemistry itself depends on quantum mechanics. But that's not quite what people mean when they talk about quantum biology. What they mean is some of these weird effects that you get in quantum mechanics, like tunneling through barriers or entanglement, where particles which are separated nevertheless have some sort of what Einstein called ghostly action at a distance, and where you can have superpositions of states. In other words, something can be both up and down, left and right at the same time. These very, very peculiar, weird quantum effects do, in my view, play a role here and there in life. And the sort of examples that people have discussed are improbably bird navigation, the avian compass. Some birds are able to detect the Earth's magnetic field, and there seems to be some good evidence that they're using quantum effects for that. But there are probably half a dozen examples of quantum mechanics being really important in a biological process. And the big question for me is, are these just a few quantum quirks? In other words, you might expect life, which is so good at optimizing what it's doing, to have stumbled onto various quantum effects over the billions of years and made use of them. Perhaps if you gain an edge by using quantum effects, maybe it doesn't have to be much, maybe 20% enhancement, but nevertheless it will be selected for. And is that the case, that life has just discovered and deployed a few quantum tricks? Or is life fundamentally quantum mechanical? In other words, will we never understand it without taking into account some non-trivial quantum nature? And I have a sneaky feeling that it's the latter. I can't prove that, but I think I want to go a little bit beyond that and not just say, well, it'll all turn out to be, as Schrödinger, I think, really hoped, all turn out to be explained by quantum mechanics. I think we, along with Schrödinger, I believe in this new kind of physical law, and it'll be where the quantum mechanics sort of meets the classical world of ball and stick chemistry, somewhere in the realm of molecules complex enough to behave like the sort of tables and chairs of the everyday world, and yet still small enough to touch the quantum regime. So it'll be sort of on the edge of that transition, which is where I believe there will be new laws of physics, and these laws of physics will involve the way information is managed, and that's where the secret of life really comes from. So this is really little more than a vision at this stage. I don't have any evidence. I occasionally talk to colleagues and discuss possible experiments to probe this regime. But of course, it's technologically very hard. Otherwise, we know about this already. What I'm talking about is looking for subtle quantum effects and maybe post-quantum effects in systems which are already pretty complex and which are in an environment that might be warm and noisy in the sense of external disturbances. Very hard to actually do experiments in that regime. Hard, but not impossible. And there are certainly people trying to probe that place where transition from the quantum to the classical world, and trying to probe where in the hierarchy of molecules, starting with hydrogen, the simplest, up to DNA, where will we see the transition from the quantum world to the more everyday classical world. So this is all for the future, and I hope we have some young people listening to us today, because I think a career in science is fantastic, and if I was to start again, I would go into that area where physics, chemistry, computing, and information theory and nanotechnology all converge, because it's there that the surprises are going to come. It's there that the new kind of physical law that Schrödinger presaged is going to be discovered.
This is interesting because I guess you could say, and correct me if I'm wrong, this sort of parallels the non-living universe in that, yes, we have this world we describe with general relativity and everything else, but quantum mechanics doesn't go away at this level. It just becomes more obscured, and quantum effects still happen even in the world of the big. So is it that far of a stretch to say that it could be involved in life? So I don't know that it would surprise me that quantum mechanics would play a role in both the genesis of life and the functioning of life. But what is, now, to switch gears to a greater question, the universe itself, and a lot of people have pointed this out, seems fine-tuned for life. Do you think it really is, or do you think we just got lucky somehow, just then that there may be other universes that are better for producing life, and we may live in one that only marginally so, or there may be even worse ones. Do you think that's really the case, that it's just this fine tuning is chance?
Well, that's a fascinating question. And in particular, your question, could we do better? In other words, the universe is good at life, but could it be better at life? I've actually written a chapter on that in my next book, which is called What's Eating the Universe, and that will be out in September. So it's very much in the forefront of my mind. But to address the more general question, is it fine-tuned? I don't think there's any doubt that some of the parameters in physics, really, if you change them by very much, it would wreck the chances of life. And I like to explain this by saying, imagine that you wanted to play God and you had a designer machine with knobs on, and you could dials, and you could turn these dials and change some things you didn't like. So turn this dial and you make all electrons in the universe a bit heavier, and change that one, you make the weak force a bit weaker, and so on. Now, of course, we can't do the real experiment, but we can do the thought experiment. We can calculate, what if everything stayed the same, but electrons were 10% heavier or something like that. We can work out the consequences for certain things like the nature of stars and so forth. And what you find that for some of those dial settings, even the slightest little change would basically wreck the chances for life in the universe. They would have literally lethal consequences. Now, that's not true of some things, the strength of gravity, for example. Life isn't very sensitive to that. But there are examples, and when you put them all together, it does make the universe look like it's rigged in favor of life. Now, is this evidence for some sort of big fix? Well, scientists are pretty wary of any idea of a big fix, and they don't like the idea of a cosmic fixer. And so that theological interpretation that the universe was designed for life by a physicist God who got the numbers right, I think is anathema to many scientists. And so they have retreated. Many scientists now, I think, take the point of view that what we've been calling the universe all along is really only just one component in a vast assemblage of different universes, which is usually called the multiverse. The idea here is that there was a Big Bang, brought our universe into existence, but there are many bangs going on scattered throughout space and time, and this whole assemblage is eternal. And so there's an infinite number of universes to go round. Now, if you put that together with the idea that the laws of physics are not fixed, they're not immutable, that there are some accidental features to it, just like there are accidental features, say, to the solar system, number of planets or something, which way they're spinning, all these things just accidental, that maybe the laws of physics are like fossils from the earliest, hottest time of the Big Bang. And the other Big Bangs would have different fossils. And if you take a sort of God's eye view and look across this vast assemblage of different universes in the multiverse, you'd find all possible arrangements of laws instantiated somewhere. And of course, in a rare subset of those universes, the numbers would come out just right for life. At least there'd be a narrow range. Of course, it's never a precise thing. And then that leads you to the question, well, might there be places that would have more life because those numbers were more favorable? And the evidence, there's a physicist called Fred Adams who took a look at this, and he concluded that yes, we could redesign the universe. If we can make our own universe, we could make it to be more life-friendly than the one we're in. So all these are fascinating questions. The problem is it's very hard to test. You think, well, how do we know there are these other universes, and how do we know they could have different laws and so on? We can't observe them. This is just a sort of mind game. Is there any way at all that we could test some of these ideas? And it's very hard. The tests are really rather weak. But there is one that I'm impressed by, and that's if our universe is somehow typical of life, we would not expect to find it on the edge of the window of opportunity. We'd expect to find it, in some typical position in the middle. In other words, that when we look at the values of those parameters, we would not expect our universe to be one in which life just squeaks home, we would expect it to be sort of somewhere in the middle of the distribution. Now, we don't know that yet, but what it does suggest is that as we find out more and more about the strength of, say, dark energy and those sort of things that life is sensitive to, that this prediction that will be more and more typical will be verified, and that would be weak evidence in favor of a multiverse. But it's not a lot to go on, and a lot of people are just skeptical about that whole line of inquiry.
But it also creates another question, is that if there isn't a multiverse and this universe is all that there is, which I guess is the definition of universe, it starts to look a little strange, doesn't it? Because then you have this weird random occurrence of life and consciousness, essentially the universe perceiving itself. Does that seem to start looking a little bit fake?
You're quite right that if there's just one universe, if this is it, then the laws that it came with, and if these laws are fixed, which is the conventional position, they were fixed up to bring forth life, or at least they were fixed up to be consistent with the emergence of life. It could so easily have been different. Just saying, well, the laws of physics explain life, that's, as we've already discussed, there's much more to it than that. But the laws of physics that we know and love are certainly consistent with life, and that does look a little bit contrived. However, this conceals a deeper problem, which is we have no idea where the laws of physics come from in the first place. The conventional view is that they were imprinted on the universe to the get-go, the Big Bang that started it all off, that those laws were there at the outset, they're immutable, they're universal, they're eternal, they don't change at all, and whatever happens in the universe, however violent the phenomena, the laws are impervious to that. We don't know where they came from. And most scientists think, well, that's not a scientific question. That's beyond the scope of science. We just accept the laws are as they are and get on with the job. But if you really are seeking a final explanation for the universe, if you want a closed and complete explanation of existence, you can't just shrug aside the laws and say, well, that's just the way they are. You have to ask, how can we explain that? Is it possible to bring the laws within the scope of scientific inquiry as a legitimate study? It's normally considered just beyond the pale. It's outside of science. I don't think we should give up on that, but there's very little point in doing that if you think that the laws are absolutely fixed and nailed down. It's only if you would allow for there to be some flexibility, and possibly even flexibility over time. The idea that the laws have been the same from the first moment of existence to they are today, we don't have to stick with that. That's the original idea. It goes back to Newton. It's essentially a theological idea, because Newton, like his contemporaries, thought that the laws of physics were thoughts in the mind of God, that they were God's laws, and that because God is immutable and eternal and so forth, it reflected God's nature. Whereas the world, the creature, not the creator, but the creature, doesn't have to be as it is. In other words, the laws are necessarily as they are because God necessarily is as God is. And so that theological basis to the laws of physics was taken up by Newton and others, and it's still there in fundamental physics. There's still that essentially theological assumption. But it may be wrong. It may be that this is, after 300 years, that we should give up the idea that these laws are totally nailed down and immutable, and that we should entertain the possibility of laws that change as over time, or more to the point what interests me, as a function of the state of the system. That there may be different laws for different systems depending on their state. And that's a sort of radical suggestion that I've been working on myself with colleagues in recent years to see whether that offers new pathways to complexity, and in particular pathways from non-life to life, by allowing the underlying laws themselves to evolve with the state of the system. So I don't have any evidence for this. This is just an idea of what John Wheeler, who hated the notion of immutable laws himself, he used to call it an idea for an idea. So it's still in its formative stages.
Wouldn't inflation suggest that that's correct, that things do seem to change?
Well, inflation, we should explain, is an attempt to explain why the universe looks so uniform, why indeed that we can even talk about this thing called the universe, because when you look out at the night sky, you look far enough, it's the same in every direction and out at great distances. Take a blob of space, big blob of space, it's much the same as the big blob of space in our neighborhood. Everything looks very much the same. How did it get set up in astonishing state of uniformity? The most striking example is the cosmic microwave background radiation. This is the fading afterglow of the Big Bang, the heat left over from that originating event. It bathes the universe at a temperature of a little under 3 degrees above absolute zero, and that radiation is astonishingly uniform across the sky. If I look to the right and compare it to the left, there's a variation of no more than 1 part in 100,000. So how did the universe get itself into this very, very smooth condition in the first place? Inflation seeks to answer that by suggesting that just after the original Big Bang, when the universe came into being, in that first split second, it leapt in size by some enormous factor, staggeringly huge factor, so that any irregularities would have been smoothed out, much as when you inflate a balloon, all the crinkles go away. So I like to say it's as if the universe started out and it was a bit of a mess, and then it took a huge deep breath and everything got smoothed out. And so inflation explains the uniformity of the way matter and radiation is distributed in the universe, but it doesn't explain the uniformity of the laws themselves. To get inflation to work, you have to assume that the laws of gravitation and the laws of quantum mechanics were the same in that first split second as they are today. And when I say split second, I'm talking about a trillionth of a second. You have to assume the same laws of that little sliver of time as all these billions of years later. And so that's a huge extrapolation. And it's very fashionable to suppose that was the case. But we can question whether we're really allowed to do that, to take laws as we determine them today and project them all the way back to that first sliver of time. Not sure that's true.
Now, we have to take a break, but I want to call attention to some of your books on some of the subjects that we just covered. And you can find them on Amazon, and they include The Mind of God, The Scientific Basis for a Rational World, The Goldilocks Enigma, Why the Universe is Just Right for Life, and The Demon in the Machine, How Hidden Webs of Information Are Solving the Mystery of Life. We'll be back in a moment. And we're back with Paul Davies. Now, Paul, another thing that people talk about, particularly recently, is simulation theory, that the universe could be a simulation. Do you have any thoughts on that?
Well, I have lots of thoughts about are we living in a computer simulation, because it's one of these things that superficially it seems completely nuts. But on the other hand, when you start digging a bit deeper, the arguments are very persuasive, and I think we have to take them seriously. The argument, let me just outline it, goes something like this. Increasingly, we're getting computers that can outsmart us, not just playing chess, but in pretty advanced intellectual activity, decision-making in complex systems and so on. I don't think anybody would say that a computer that we have now is literally conscious. But I think a lot of people believe that within a few decades, we will have, whether it's a robot or a computer, or we lack the words, but a system which processes information, and AI, artificial intelligence, which would, as far as we can tell, be as conscious as another human being. You can never know that another human being is conscious without being them. So we sort of infer that from their responses. And we could well get to that situation within a few decades. So if you have the possibility of machine consciousness or artificial consciousness, then you can, of course, provide that artificial consciousness with a virtual world, with virtual reality. We know how to do that. And so it's a small step from that to imagine that you might have an entire community of conscious entities inside some super-duper information processing machine, inhabiting some sort of artificial virtual world. And these entities themselves would not know that they're part of a simulation. They would just be having their experiences. So if you think that consciousness is a physical phenomenon and not some sort of magic, then obviously in principle you can recreate it, you can simulate it. And so then it's a simple step from saying, well, how do we know that we are not simulated beings inside some super duper computer at some other plane of existence? And the answer is, well, we can't really know that. We can imagine, we might be scared about that idea on the basis that the simulating system might decide to put an end to the whole thing, and we could suddenly be shut down. That's sort of an alarming thought. But the argument for why we should take that seriously is a sort of curious one. We've been talking about the multiverse earlier, the idea that there isn't just one universe, but maybe an infinite number of universes, and that at least in a subset of those, there will be conscious beings. But now you have to add to these, if you like, real other universes, the possibility of other simulated universes or fake universes. So if you take a given universe, in principle, we could create an entirely new universe of our own. We could use the laws of physics to create a Big Bang and make another universe. But it's far cheaper for us to make a simulated universe, a fake universe, if you like. So if the fakes are much cheaper than the real thing, then you might imagine, when you take this God's eye view and look at this whole multiverse, that among all these real other universes, there would be a much greater number of fakes. And therefore, a randomly chosen observer would be overwhelmingly likely to find themselves living in a fake universe rather than a real one. And so unless you have reason to believe that you and I are not typical observers in this vast assemblage of universes and minds, if we think we're special in some way, that's different. But if you think we're just typical, then the odds are that we're living in a fake universe, a simulated universe. So that's the way the argument goes. Now, of course, it's not totally watertight, and some people just sort of throw up their hands in horror and say, well, this is self-evidently absurd, this whole line of reasoning. But actually, it is a persuasive argument. I'm not saying that I believe we're living in a simulation, but I think we have to take seriously the reasoning. And if we're not, then which of the things that I've mentioned before is wrong? Is it that there aren't an infinite number of universes, or that consciousness is something that can't be created? It's not a physical process. It's something added on to the universe in a way that human beings couldn't do it. Or do we misunderstand notions of infinity, so that when we're doing the statistics here, we're not getting it right? There's all those sorts of assumptions that go into this argument, but I think we do have to take it seriously. And like a lot of these philosophical arguments, that they have a sort of absurd aspect to them, but they point to deep issues which are well worth reflecting on. And I might say that this idea that the universe is a simulation is not a new one. René Descartes in the 17th century said that we had this idea that there might be a malicious demon who was planting impressions in our minds, and that the universe we see isn't the real one, it's a fake one being created by this demon. How will we ever know? And so these are powerful arguments that go to the foundations of the very notion of doing science and the very notion of a rational world and rational explanations for things. We have to think about them, but that's not to say we sort of rush out and embrace them. It's important that these thought experiments lead us to reflect on how the universe is put together and what assumptions we're making when we try to explain things.
As a related and possible mechanism for the universe, or at least a simulation, what are your thoughts on Boltzmann brains?
So the Boltzmann brains is a similar type of idea. And again, let me just explain. So first of all, who was Boltzmann? Well, Ludwig Boltzmann was one of the founders of the theory of thermodynamics. And so he was interested in how heat flows from hot to cold. And we now know that molecular activity is a measure of heat. The molecules rush around faster, it's hotter. And so he looked at how molecules banging into each other exchange energy, and he came up with a concept called entropy, which is a measure of the degree of disorder in a system. But of course, he realized that there would be no flow of heat in the universe at all, unless the universe had started out in a much more orderly or low entropy state than it's in now. And because the second law of thermodynamics, of which he was the architect, says that entropy can only go up, disorder can only increase, how did the universe ever get itself into an ordered state in the first place? So he had a curious explanation for that, and its analogy is if you take a deck of cards. I'm told this, I've never actually checked, but if I go down to a local store here in Phoenix and buy a new deck of cards, when I open them, I'll find that they're arranged in suit and numerical order. That's the folklore. And so if you shuffle the cards, they will be less ordered, and afterwards there'll be a jumble. Now, if you went to a magic act and you gave the jumbled deck of cards to the magician, who then shuffled them, gave them back to you in suit order, you know you were being tricked. However, it's not strictly impossible to shuffle the cards back into their original configuration. It's just exceedingly unlikely. And now, if you think the same thing with gas is, can you get back to the state you were in initially? Imagine a box of gas with all the molecules in one corner, and you let it go, they rush out, they fill the box, and then the gas just sits there. Is it possible that they could all rush back together into that corner? Well, the answer is, like shuffling cards, it's not strictly impossible, but it's exceedingly improbable. And so Boltzmann had the idea, well, this must have been how the universe got itself into an ordered state in the first place. There was some gigantic fluctuation from thermodynamic equilibrium. It was necessary in order that there should be conscious beings, and the fact we witness this near miracle is because it's a prerequisite for our very existence. So that's the idea, why it's named after Boltzmann. But the point is this, that if the universe endures forever, we don't know that's going to happen, but supposing it goes on forever and ever, then given an infinite time, is it not possible to have these near miracles occurring? Because in an infinite time, even the near impossible is going to happen, and happen infinitely often. So is it possible that a brain could be reconstituted out of next to nothing and come into existence and have experiences and then dissolve away again? From what we predict about the very far future of the universe, it's likely to be just sort of empty space with quantum fluctuations. But the very fact that there are quantum fluctuations means there's a sort of randomness to it, like shuffling the cards, and out of this quantum ferment, it's possible in principle for something like a brain to come into existence. It wouldn't last very long, but it does raise the question of whether, we're back to this numbers game, if you are an arbitrary observer, what is more likely, that you'll be living on a planet some few billion years after the beginning of the universe, or is it more likely you're going to be a Boltzmann brain, untold trillions of years in the future, being constituted from this quantum vacuum? And again, when you put the numbers in, it looks like experiences would be Boltzmann brains every time. They would infinitely outnumber the non-Boltzmann brain type observers. So it's another one of these philosophical arguments that you don't necessarily have to believe it, but it calls into question the underlying assumptions that you're making in your cosmological model or your physical model or your model of the nature of consciousness. All of these things go into that mix. And this is taken seriously enough that there are entire conferences devoted to the question of Boltzmann brains. So we're here dealing with, I don't know what used to be called ironic science. We're examining the conceptual foundations of these really profound subjects like cosmology and fundamental physics and the nature of physical law and so on, and the nature of consciousness. All of these things are very deep, very important, and not totally understood. And we're examining those conceptual foundations by a variety of thought experiments or a variety of scenarios where if you believe that the world is rational and that ultimately there are reasons for why things are as they are and that it should hang together in a rational way, well then these types of discussions that we've just been having form an important part of saying, have we got all this right? Have we got the right framework for approaching these problems? And again, being a heretic, I'm going to say, I'm not sure we have. I'm not sure. I think that some of these problems of things like Boltzmann brains means that we're probably thinking about the universe in the wrong way.
Now, to go from the huge scope of the universe down to the small in regards to life, if life is very rare or even unique to this planet in the universe, then doesn't that start to create questions about the origins of life on Earth? Because as far as we know, or as far as we can see, life seems to have begun on this planet just the very first moment it could. But then there's Mars. Do you think that if life is rare, then our origin is probably more likely to be on Mars?
I've always been fascinated by this idea that life on Earth may not have started on Earth. And I think part of the reason for that is my early exposure to Fred Hoyle, who was a famous British cosmologist who also dabbled around in the origin of life. And he's one of these genius people who had many, many wonderful ideas and many, many crazy ideas. But he certainly believed that life could travel across the universe. And so that sort of stayed with me, that idea. But to come to your point, that life did get going on Earth really rather rapidly. Earth is 4.5 billion years old. There's evidence, good evidence for life in the hills in Australia going back 3.5 billion years, and some possible evidence from before that. And so there's been life on Earth for a greater part of its existence. So there are two explanations. One is, well, life is easy, pops up all over the place. It's no surprise it started quickly. I'm not convinced of that. So the other is, well, no, actually, life is really hard to get going, and you need as long a period of time as you've got. So can you extend that period of time? And within the solar system, I think the answer is yes. It's possible life started on Mars and then came to Earth in a meteorite. And now how does this happen? Well, from time to time, Mars and Earth are hit by big rocks, asteroids, comets, with enough force to splatter material all around the solar system. And Earth rocks go to Mars, Mars rocks come to Earth. There's about 6 Mars rocks in the meteorite collection here at Arizona State University. So these things are now known. They weren't 50 years ago, but we now know of many, many examples of Mars rocks coming to Earth. So if Earth and Mars can trade rocks, can they trade organisms, microorganisms only? Can microbes living inside rocks be transferred from Mars to Earth or Earth to Mars? And I suggested that idea back in the early 1990s, and it was met with total derision. I might say that there was an occasion where I was even denounced for this idea in the after-dinner speech at a conference in London. It's one thing to be criticized during a lecture, quite another to be picked on during the dinner speech. But anyway, it very soon became clear that what I was suggesting is in fact the case, that it's entirely possible for life to make the journey from Mars to Earth or Earth to Mars. So that raises the question about whether maybe life started on Mars and came to Earth inside these rocks at a later stage when Earth was suitable for life. So it was incubated on Mars. Why is Mars more favorable than Earth? Well, it's not an overwhelming case, but it's a smaller planet, so it cooled quicker and was ready for life sooner. And that's important because the bombardment I've been talking about was really ferocious in the early days. And the best place for life to be is actually deep under the ground in those circumstances. We now know there's life under our feet going down to maybe 5 kilometers. Pretty much everywhere you drill, on land or beneath the ocean, you find life living in the rock underneath. So the biosphere is not just a veneer on the surface of the Earth, it extends deep down into the crust. The same would have, if there was life or is life on Mars, would be also true. It would be in the subsurface. But it would be possible because Mars cooled quicker for that subsurface life to be deeper sooner. So in other words, it was a great place to shelter from the effects of that bombardment. So the bombardment, which would have propagated life between planets, also threatened its existence in the early days. So that's the sort of general argument. In a way, this would be disappointing. The question that we've been addressing throughout our conversation is really, is life a fluke? Is it something that maybe happened just once, just a gigantic chemical accident? Or is it somehow built into the laws of the universe? Is the universe literally rigged in favor of life, so life pops up wherever you want it? And we could answer that question if we had a second sample of life. That's what we'd really like. We'd love to go to Mars and say, yes, life happened on Mars as well. So therefore, 2 out of 2 in the solar system is pretty good odds. The universe must be teeming with it. The universe must be rigged in favor of life. But sadly, Mars is compromised because of this exchange of material. We might well go to Mars and find there is or was life there. It's just boring old Earth life. It's just the same life, but we know there's still only one sample of it. We'd like a second sample of life to be able to settle this matter. As a matter of fact, we don't have to go to Mars even to find a second sample of life. It's possible that there's a second sample of life right here on Earth. We just overlooked it. That in the microbial realm, the vast majority of those little critters have not been cultured or characterized, let alone sequenced. We don't know what they are. It's possible that intermingled with the microbes that is our form of life, the life we know and love, is descendants of a second genesis that would have occurred, or many geneses would have occurred right here on Earth. So whether you go to Mars, whether it's on Earth, whether it's somewhere else, like in Enceladus or Europa or outside of the solar system, what we really want is a second sample of life. Because when you've only got one, you can't be sure that it's not just a freak, not just a result of a dream run of chemical processes that just happened once and we are it. That's why I attach such enormous importance to looking for life beyond Earth. Just one microbe beyond Earth, or even here, as I've said, on Earth in some sort of shadow biosphere. Just one microbe that is life, but not as we know it, would suffice to make the case that the universe is indeed teeming with life and the laws fundamentally life-friendly.
Europa would seem to me, one, because of the ice shell, and two, because it's further out, would seem to be less subject to transpermia, right? So that
Yes.
might be, if we found life there, that might be a better chance than Mars for finding a truly independent occurrence of life, right?
Yes, in the early days when I was touting this idea of the Mars-Earth exchange, it seemed to me that that was inevitably the case, that these outer moons of the solar system would be protected from that. But calculations have been done in recent years that show that it's not totally impossible for Earth rocks or Mars rocks to get out to Europa or Enceladus. And of course, it's one thing to get there. It's another thing for life to be able to gain a foothold. If a rock falls on the icy crust of Europa, you believe that the conditions beneath the ice are conducive to life. Well, then somehow the rock has to get there. So it's far less probable. In the case of Earth and Mars, I think it's absolutely inevitable, particularly that when this bombardment was at its fiercest between 3.5 and 4 billion years ago, Mars and Earth were very similar. Mars was warm and wet and probably had a thick atmosphere. So if Earth life went to Mars, or the other way, Mars life came to Earth, it would have been similar conditions. So it would have been a congenial habitat to set up home, a new home. That would be far less likely, I think, on these icy moons.
Now, one last possibility for answering the question is here on Earth in the laboratory. When do you think, or do you think it's ever going to be possible for scientists to create artificial life and crack the mystery of abiogenesis that way? Or do you think that's a pipe dream?
Well, it's there's a lot of terminological confusion around this because people will often say, oh, we've already created life in the lab. Didn't Craig Venter create a novel microorganism many years ago in which he basically designed his own genome and even inserted his email address according to the folklore, uploaded it into an existing microbe and then sort of booted it up, and it's called Mycoplasma laboratorium. Well, that's re-engineering existing life, or if you like, it's rewriting the software. So coming back to my computer analogy, it's like saying, well, I'll take the computer, thank you very much, but I'm going to rewrite the code and tweak a few things with PowerPoint, put in a few new features. So it's possible right now to edit life, but not to create it from scratch. And where it's hard to express just how far we are from the idea of going from simple mix of chemicals to something which is a truly autonomous living thing with all of its software and hardware coupled in such a way that it can make a living on its own without external manipulation. We're so far from that. But even if it were possible, we can imagine that, maybe in 1,000 years with fantastic technology, it were possible to actually step by step put together a living organism. Would that explain how life got going on Earth or Mars or wherever, the life that we now know? Would that explain its origin? And the answer, I think, is no. It's one thing to have fancy equipment and a well-stocked lab, and more to the point, an intelligent designer, also known as a clever scientist, knowing what they're trying to achieve and putting it all together. It's one thing to expect that to happen as a deliberate process. Quite another to say how it happened in the sort of grubby, random circumstances of a prebiotic planet. So even if we can make life in the lab, it wouldn't necessarily explain how it happened in nature. But it would give some important clues. And in particular, I said earlier, we have no idea whether the pathway from non-life to life is one of these things that's inevitable given enough time and the right circumstances, or whether it is so fluky it's only going to happen once. If you could make life in the lab and then say, well, actually, this is pretty easy. We can vary a lot of the conditions, a lot of the parameters, and yes, we still get to life. In other words, it's a broad path from non-life to life. If you could establish that, that would, I think, very much help. But all of this is so far in the future. It's so speculative, creating life from scratch, not just rearranging things, starting it from scratch without step-by-step intervention in a very careful way. We're so far from that I don't think any people listening to us now are going to be alive if and when it happens.
And we are out of time. Today we were joined by Paul Davies, and Paul has a book coming out in September entitled What's Eating the Universe? Look for it. Thanks for listening. I am futurist and science fiction author.
Wrong channel.
No, it's not. Thanks for listening. I am futurist and science fiction author John Michael Godier, currently hosting Event Horizon and wondering where Anna actually came from. One day I had a tablet computer, the next I had a boss. Very disturbing. And be sure...
And that's enough of that.
YouTuber forever! Like, subscribe, and hit the bell!
Sell out.
What?